A man is pulling two boxes, one on top of the other, on a flat horizontal surface by pulling on a rope parallel to the surface. A horizontal rope, I guess, right? The coefficient of kinetic friction between the floor and the lower box is 0, this is mu k, is 0.344, and the coefficient of static friction between the two boxes, mu sub s, is 0.751. What is the magnitude of the maximum acceleration the man can pull the boxes without having the top box slip off the bottom box? So you're asked for acceleration, and he's got some pulling force. You're not asked for that pulling force, but basically we will assume that both boxes have the same acceleration. So I think all we need to do is draw the free body diagram for the top box. So that's going to be the normal force on, if we call this 1 or something, and this 2, we'll call this normal force on 1, m1, g pulling down, and then there'll be this static friction force pulling to the right. We're finding maximum acceleration, so set the box to be just about to slip when mu sub s times n1 is that friction force. If we define y to be up and x to be down, and a sub y is 0, means that the net force in the y direction is 0, which is n1 minus m1g. So this means that n1 equals m1g. F net in the x direction is equal to m1 times this acceleration that we're trying to find. So we'll say that m1 times a is equal to fs max, which is going to be mu sub s times the normal force, which is m1g. And the m1s cancel in this, and you get the a is equal to mu sub s times g. So it's 0.751 times 9.8. 0.751 times 9.8 equals 7.36 meters per second squared. D. A steel suspension cable is used to support a gondola at a ski resort. The unstretched length of the cable, I think this is going to be a Young's modulus question, so let's write L0 is 4,300 meters. The diameter of the cable is 3.6 centimeters, so we're going to need a radius in meters there. The Young's modulus for steel is 210 times 10 to the 9 newtons per meter squared. If the cable is under a tension, so there's this force here, I guess, is going to be 2.1 times 10 to the 6 newtons. What is its change in length? So need delta L. If I look at my aid sheet, I've got 1 over y times F over A times L0. So we need to find A. So the first thing I would note is that if the diameter is 3.6 centimeters, you divide that by 2 to get the radius. Let's not forget that. And then also let's divide by 100 to convert centimeters to meters. So 0.018 meters. And the area of a circle, I assume this is a circular cross-section here, is pi times r squared. And so A is equal to 3.14159 times 0.018 squared. So square that and times it by 3.14159. And I get the area is 1.018 times 10 to the minus 3 meters squared. And so delta L is just going to be 1 over 210 times 10 to the 9 times the force here is 2.1 times 10 to the 6. The length is 4,300, and then divide it by the area, which is 1.018 times 10 to the minus 3. Let's plug all that into my calculator. 2.1 times 10 to the 6 times 4,300 divided by, open parentheses, 210 times 10 to the 9 times 1.018 times 10 to the negative 3, end parentheses, equals 42.2 meters. That's closest to E. An empty box is on an incline and it doesn't slip. What happens if you steadily add rocks to the box, increasing its mass but keeping the same surface in contact with the same incline. So this has got some mu sub s, and it's got some angle theta. And we found that the maximum angle theta before it starts to slip depends on mu sub s. So if it's not slipping, it doesn't matter. Changing the mass does not change the slip angle. So if it doesn't slip with a small mass, it's going to not slip with a larger mass. A block of mass m is 2 kilograms is placed on a horizontal surface. The coefficient of static friction between the block and the surface is mu is equal to 0.40. A light rope is attached to the block and threaded over a frictionless pulley as shown, so that the angle that the rope makes with the horizontal is theta is 52 degrees. The free end of the rope is pulled with a slowly increasing force of magnitude t. At what value of t will the block start to slide along the surface? Okay, so and we have to write this on the this problem on this written problem answer sheet. So first thing I'm going to do is sketch and translate. So I always like to redraw the problem. I've got a box here, and this is this tension force, and here's this angle theta, so there's tension. And what's happening is we've got mu sub s. So tension is what we need to find. We need this. We're going to assume that a block does not slide. So what that's going to mean is that the sum of all the forces in the x direction is equal to 0, and the sum of all the forces in the y direction is equal to 0. It's an equilibrium problem. That's good. We're also going to assume that it's just about to slip. Okay, so what that means is that F sub s is equal to mu sub s times the normal force. So we're going to have to find that normal force, find the static friction. And I think that's about it. So the simplify and diagram step is going to involve, let's draw a force diagram for that object. So again, there's tension, and there's theta, by the way. There's a normal force that's acting upwards on it from the surface. There's a static friction force, which I think has to act that way, to the left, to counteract the tension. And then there's, of course, gravity acting down. And so what we're going to do is define, I guess, plus y is up, plus x is to the right. And by the way, I've added in the numbers. I guess that's probably good to put in the sketch and translator somewhere. And then, yeah, let's do our force balancing equations. So I guess one thing I need to do at some point is decompose the tension into two t sub y and t sub x. I think those are both going to be positive. But so maybe I can do it over here. I think t sub x is going to be equal to the t times cosine of theta, and t sub y is going to be, and that's positive, plus t sine theta. Okay, so the sum of the forces in the x direction is going to be equal to t times sine theta minus the f sub s. And so those are going to be equal. So t sine theta, and I can plug in my equation here, is equal to mu sub s times n. So that's one equation. And then the sum of the forces in the y direction is going to be the normal force plus the t cosine theta, those are upward forces, minus mg. Sorry, that equals 0, and this is equal to 0. So this will tell you that the normal force is equal to mg minus t cos theta. And this is equation 2. So our next step represent mathematically our strategy here. We don't care about n, so we're going to eliminate n and solve for t. So from 1, we've got t, equation 1, t cosine theta equals mu sub s, and then times the normal force. And so from equation 2, we've got mg minus t sine theta is the normal force. And so we can multiply through by mu sub s times m times g minus t times mu sub s times sine theta. Okay, Now we're gonna, and that's equal to t cos theta. Now we're gonna gather all the terms that have t on one side of the equation. So I've got t cosine of theta plus t times mu sub s times sine theta equals the things that don't have t on them on the right-hand side, mg. Now we can pull out a factor of t on the left-hand side, and I've got cosine theta plus mu sub s times sine theta equals mu sub s times mg. We got to finally get an equation for tension, which is what we're trying to find. It's mu sub s times m times g, all divided by cosine of theta plus mu sub s times sine of theta. So mu sub s is 0.40, multiplied by the mass is 2.0 kilograms, multiplied by g, which is 9.8, divided by cosine of 52 degrees plus 0.4 times the sine of 52 degrees. 0.4 times 2 times 9.8 and divided by, open parentheses, 52 cosine plus, open another parentheses, I'll do 52 sine times 0.4, close parentheses, equals 8.42. Tension equals 8.42. That is in newtons, and I'll put a box around it, and that is my final answer. My name is Jason Harlow, and I hope you enjoyed this video. If you have time, please fill out the feedback form on my Google Forms available in the description to this video. There's also a link to the Google Classroom where there's a public discussion forum and a place where you can ask me a lot of questions. Also available as a link in the description to this video. I look forward to hearing from you. Take care.